Okay, next I'm going to talk about battery basics. In this presentation today, I'm going to talk about lead-acid batteries, the LFP battery that's making its way around, which it will come back. I have great confidence. I'm going to talk about USB power banks. Okay, so lead-acid batteries, the advantage, if we have an EMP blast, they're still going to probably work. They're wide availability during a disaster, cheaper price. They've been around for a long time. But they do have some disadvantages that we all know about. How heavy can they be? Now this is a 55 amp hour battery, and I used to have a 100 amp hour battery. If any of you lifted a 100 amp hour battery, do you know how much fun that was? Okay, so I'm getting a little older now, so what I'd like to do is just restrict myself to about 55 amp hours. And if I want 100 amp hour, I'll just parallel a couple. Okay, so the thing about lead-acid batteries is they really need to be topped off all the time. You just can't use them, put them away, and then come back and then charge them later. They can have some problems. They don't have a lot of energy, and they have a much shorter life cycle than the LFP batteries. These batteries may be about 50% depth of discharge. You're getting about maybe 500 cycles. Whereas the lithium iron phosphate, the new battery, you get 2,000 cycles. I can go down to 50% depth of discharge. In those, I can do 90 to 100%. Now, it takes more time to charge these batteries because I can go in the bulk charge mode. But then that topping off charge, I have to go really slowly to finally get it to 100%. And if I have a flooded battery, I have the issues of the hydrogen and the oxygen happening. I need to replace water. And if I spill them, I made a big mess with my sulfuric acid. Okay, all right. Okay, so how do lead-acid batteries work? How is that happening? So you have your negative plate and your positive plate. And the negative is the porous lead, and there's these sulfate ions that are in solution, and they carry 2 electrons, and it comes over and approaches that lead negative plate, and those electrons cross over, and it makes lead sulfate. So I have lead sulfate building up, and those 2 electrons go through the circuit, and they come over to the positive side, and on the positive side, those 2 electrons come down to the lead dioxide plates, and I have hydrogen ions and sulfide ions, and those 2 electrons come over into the solution. We have some reactions happen. We make water and lead sulfate. So my negative plate and my positive plate are both building up with lead sulfate, and that's the normal reaction. Now the lead sulfate is in a soft form when I first am getting it. And then if I don't charge the battery back up, it can go into a more hard form, the crystallized form. Now batteries are going to be really important if we suffer a major grid outage. So the questions I'm going to be asking myself is, how full is the battery that I'm starting out with? How much capacity? And then the real important question, how quickly can I charge my battery if I'm dependent on the sun? Because the sun doesn't shine that long in the wintertime. So I want to be able to have the ability to charge my battery very quickly, or know how fast I can charge my battery. So if I'm looking at the state of charge for lead-acid batteries, it's approximately around 100% state of charge at 12.6 volts. At 12.4, it's about 75%. 12.2, 50%. And 12.0, 25%. Do you see a pattern there? For about every 0.2 volts, my capacity is down 25%. What that also means is if in my system, if I lose voltage, it's the equivalent of losing capacity from my battery. So this was a battery that was at 77 degrees Fahrenheit, and I just pointed out for every 0.2 volt drop, it's 25%. Now, most of our radios, as you know, require the low of 11.7. So what you have is 12.7 is my fully charged battery, coming down to 11.7. I have about this 1 volt window. I have to use it wisely if I'm off grid. I can't go to the grid. It's down. So think of the 11.7 to 12.7 is our window, and 11.7 volts is our cutoff voltage for our radio. Now some of you will have radios that will go much lower than that, and you'll still be on the air if folks are having problems with having enough power in their battery. Okay, so how much energy can I get from a battery? So we talk about the amount of energy is by amp hours. So mathematically, if I have 1 amp for 1 hour, that's 1 amp hour, or 36 coulombs. Or if I have 1 amp at 10 hours, 5 amp at 2 hours. But we have to be careful with our math, because people will think that I can mathematically do these equations with batteries, and there's a Pukert effect that actually is not going to let you do that. So now how they rate the batteries, pretend this was a 100 amp hour battery. They would rate it over a 20-hour period of time. So it's a 100 amp hour battery, and they would put a 5 amp load on constantly, and over that 20-hour period it's going to drop down, and then at the end of 20 hours under load the battery would be at 10.5 volts. Then we take off the load, and then it would be a rebound of the voltage to around 11.7. Now, if somebody comes up to, amateur radio operators, we interact with the community, and they love to ask us questions. So let's imagine someone comes up to you and says, hey, mister, how many electrons go through your wire on a 1 amp load per second? You've got to help these science students, help them out here. So if a 1 amp load is 1 coulomb per second, and 1 coulomb is 6.25 times 10 to the 18th power electrons, I can't say what that number is.
6.25 times 10 to the 18th.
Yeah, exactly. But that's a lot of electrons. So that's how many actual electrons go through your wire per second with a 1 amp load. Pretty interesting. Okay, now people think of batteries as kind of like a bucket, that I can pour the energy out and I can put it back in as fast as I want. Because that's what we can do with water, right? We can pour it out, put it back in really fast. Well, in batteries, they actually have a rate that you can pour or push with the battery, and it's called the C rate. And the C is your amp hour capacity in amp hours of your battery. So let's say if it's 0.1 C, that means 10% of your battery capacity. And if I had a 100 amp hour battery and I was doing a discharge at 0.1 C, that's 10 amps. Or you would see it also listed as C divided by 10. So as you're looking up the battery specifications, you're going to see the number decimal in front of the C, or you're going to see the C divided by something. If I had 0.2 C, that would be 20 amps. So it's 20% of that 100 amp hour battery. Now let's take a look at a battery discharge characteristic. If you get a battery, you may see a chart like this, and I want to take a moment to tell you more about what it is you're looking at. So on the left, this is battery voltage and time in minutes and hours. And on the red here, you're actually seeing, so that's, if I had a 100 amp hour battery, that's 300 amps, 200 amps, 100 amps, 40%, 20%, and 5%. Now there's this dotted line at the very bottom. That's your battery cutoff point. You go beyond that, you've done real damage to your battery. You don't want to do that. But you notice the other thing about this is there's a voltage sag depending on how much your load is. So at the battery terminals, if I just do 5% of the amp hour of the battery, this curve coming back, it doesn't drop down very much. But if I go down to about 20%, which is what I'm going to recommend that you do when you're using a battery for your transmit peak load, go down about 20% of the amp hours, and you do drop some, but what we really want to make sure of is 11.7 volts coming across there. I don't want to go below that. Okay, so the batteries do have that cutoff voltage. These are just slides kind of saying what I'm talking about. And then also, it's going to really depend on the state of charge, the temperature, the age of your battery, and then we're just talking more about the amp hour. So let's say that I have this 55 amp hour battery right here, and I wanted to do some different C rates. So, I don't know, that's heavy. Can you all see this here? Folks in the back there? Okay, so what I wanted to do is show you how long you could go. So if I did 110 amps through that battery, I'm good for about 2 minutes before my radio, if I had a radio in this load somehow, would be turned off. If I did 1C, or 55 amps, so the whole circuit is doing 1C, and my radio is hooked into that circuit, it's about 15 minutes. If I did about 63%, 25 minutes. If I did 40%, 60 minutes. And if I did about 20% of my amp hour capacity, and I was hooked into that circuit, it'd be about 2.5 hours approximately. All the way down to 5% of my amp hours, it's staying above 11.7 volts for about 15 hours. That's just a ballpark number that I want you to kind of think about. And then you would actually do the calculations or run the tests yourself and see if that's close. Now, have you ever looked on the internet and had people have a little misunderstanding? Okay. Internet is great for information, but someone might say, oh, I got a 100 amp hour battery, so I can run it for 1 hour at 100 amps. And my radio's in that circuit. No, more like 14 minutes. Or I have my 100 amp hour battery and I've hooked it up to a 40 amp load and my radio's hooked into that, and I should be able to go for 2.5 hours. You're going to be very disappointed. Now, have any of you ever hooked up to a battery and went to do this and your radio turned off? You don't have to raise your hand. But I will. That's what I did years ago, and I thought, what just happened? I don't understand. That's what was going on. I was trying to draw too many amps for the size battery. So, now I want to think of a different way to visualize a battery. So I'd like you to think of that as like a water tower. Okay? So the higher I am, the more pressure, the more voltage. And let's say my water tower is about 130 feet high and it's about 20 feet on the tank. And I go up here and down here, so I'm at 12.7 volts. And then I'm down to 10.5 volts. But what happens if I drain much further? My tank gets smaller and smaller, and then I got the vertical supply pipe. So what I want you to think of is when you look at a battery, the action is happening at the very upper end of the voltage, and once it drops below 10.5 volts, you're done. So this, I want you to think of this as like a visual. It acts more like a water tank than a 5-gallon bucket. Yeah, just talking about if you drain it and then it drops like a rock. Okay, so as we deplete our battery, we may find that we're having some problems. So the remedy is we're going to have a bigger battery, use less power, larger size wire, or shorter cable length. Now, does the size and the length of my power cable make much difference? Oh, you betcha. Because if you're on solar power, everything changes. You're not hooked up to a power supply, and you're not hooked up to your car battery with the alternator running. So the size and length does make a big difference. And just real quick before I get too far in that, what I would like to recommend is at the battery that you consider a way to have a fuse for your circuit within about 6 inches. And what I would recommend is that everyone get one of these or something similar. It's an RGH-10. Here's a picture because folks are further back. And PowerWorks has these for about $15. But what this does is it fuses the battery, and now your circuit is fused. You don't have to be worrying about, what am I going to do to fuse my circuit? So let's look at some cable links and see if there's any issues. So if my, you know what's going to happen, right? So if my battery voltage is 12.5 volts, and I have a load of 22 amps, that sounds like an HF, a pretty good station going, and my cable length is 6 feet, let's see what happens depending on what size wire I use. What just happened? If I have 14 gauge wire, a 22 amp load, 6 feet, I just had a voltage drop of 0.66 volts. Yeah, remember if for every 0.2, I mean there's quite a bit of drop going on there. So 12 gauge wire, 0.42, and 10 gauge wire, 0.29. Now let's look at my VHF station. I'm not doing HF now. I got 10 amps, 12.5 volts, and between the battery and my radio is about 6 feet. Here we go. 10 amp load, 0.3 volts. 12 gauge, 0.19. 10 gauge, 0.12. That's a huge difference. For every 0.25, for every 0.2 volts, you're losing 25% of your capacity. This is almost like you're shrinking your battery capacity just because you haven't adjusted the power cable. Now, everyone knows that when I go to buy a radio, what do they put in the box for you? Okay? Can I go out and do solar power with this?
Well,
probably not. Okay, so I think this is a 14 gauge, 10 feet long. So I'm hooking up to the battery. Oh, they're good. They got the fuse at this end. This end hooks up to the radio. Can I shorten it and still use it very well? Because I lost my fuse, or I got to reconnect for the radio. Okay, so if I have a 10-foot run of 10 gauge wire, 8 amp load, it's 0.16. And if I really shrink things down from the battery to the radio, if somehow I could get that run down to about 4 feet, I'd have only a 0.064. So what we want to do is the electrons that are coming out of our battery, we want to make it easy for them to get to our radio. And if you're on solar power, you definitely want to consider changing over to 10 gauge wire in most everything. There'll be some connections you'll have to have at the terminals as a 12 gauge wire. But if you can shorten the distance, that will make a huge difference, and have a 10 gauge wire. Okay, now what's really helpful is if you want to do some calculations, there's a number of different calculators online. I'm just putting one in here. And what this will do is allow you to kind of get a feel for what the difference would be between I did make a difference, I did make some changes, and I didn't. And you can see the before and after. How much more you're going to be able to use your battery because you made some changes. Okay, now what would be very helpful is if you could look at a chart and you could see voltage, state of charge, and some certain C-rate loads to get an idea of where am I and how much am I discharging down my battery. Now on this next chart, it's going to show a C divided by 5 load down to 60% state of charge, and the voltage will still be about 11.7 volts. And what my recommendation is that when you are looking at your station, the peak load, you'll see on your inline meter what it is, that you go ahead and limit to about 20% of your lead acid battery, this is not LFP, 20% of its amp hour capacity. Let's take a look. So this chart was done by Richard Perez from Home Power back in '93, I think it was. And what you have is you have voltage here, state of charge, so this is a fully charged battery, and then they're showing different C loads coming down. Now C divided by 5, that would be 20% of your amp hour. And you'll notice as it comes down, if I can look sideways here, 60%, if I go up, it just is about 11.7. So the top 40% of your battery, you could be still having some joy while you're trying to talk. But if this didn't work out, you would have to turn down your power some. So it's just a chart to kind of get, this is just a ballpark idea. Okay, so now let's say we took this 55 amp hour battery here, and we had a C divided by 3, and I had my big 100 watt radio going, and it says, you can use about the top 8%. When it gets down to 92%, you're not going to have 33% of your battery capacity. When it gets down to 20%, you might get down to about 60% state of charge. And if you had 10%, you might get down to about 32%. Now, we don't recommend going below 50% for lead acid battery. And then C divided by 20, this would be the absolute emergency. I have to still keep talking. Sorry about this, Mr. Battery here. I'm down to 10% of depth of discharge. Okay, I just put this slide in here just to show approximately what the amperages are for different wattage settings on VHF radios. So, battery life is quoted in cycles, and it's really dependent on temperature, depth of discharge. So here you have 50% depth of discharge. It's about 500 cycles. Okay? If I was up around 30%, it's much higher. But if I did 100% depth of discharge on a lead acid battery, I might be only getting about 200 cycles. And this is assuming an ambient temperature of 25 degrees Celsius. So my recommendation, you're using a lead acid battery. You know how much your radio needs. You get approximate weighted averages, but when you do it in the field, you'll know for sure, this is just a ballpark, is try to use just the top 50% of your lead acid battery. And think of that as your available energy of that battery. So if I had a 35 amp hour battery, I want you to think of it as 17.5 amp hours. So when I'm looking at this little meter, and it's showing how much amp hours is happening, and I'm getting down to 18 and 19, I might be getting a little lower than I want to if that's the size battery I have. Limit your peak transmit. So when I key up my mic, I probably want to limit to about 20% of my amp hour capacity. So in this case, with that 35 amp hour battery, I probably am going to be okay with a 7 amp load, and that'll give me medium power on my VHF radio. Now, if you need more power, you can parallel some batteries. There's basically two ways you can parallel these batteries. If these are two 12 amp hour batteries, what you would do, these are both 55 amp hour batteries. So the positive terminals are over here, the negative terminals are over here. You could just get some short cables. If you parallel, it would be recommended they both be the same size. Don't have a long path for these electrons and a short path over here. That's not very helpful. And then you can just put negative to negative, positive to positive. And now here's the difference, is how you hook that up. You want to hook up the negative on this battery and the positive over here. If you did them both over here, you're making one of the batteries work harder than the other. Now, the other way you can do this, if I can move this, I don't want to tip over this. There's a lot of weight up here. I've got to be very careful. You can take a distribution block. This is a PowerWorks PD4. And you can go ahead and just hook it up. Okay, there's one. There's the other. We're now parallel. Now I can tap into here and have great joy. So what that's going to do when I do that, it's going to double the amp hours, but the voltage is going to stay the same. And this is just talking a little bit through what you would do and the second method. And sometimes you might do this in series, and that's where folks say, okay, I'm going to get a 6-volt battery and a 6-volt battery, and I want to do some cross connection. Now this is where you don't want to be confused, because if I cross connect here, what did I just do?
Make a
I short-circuited everything, and there might be a little more energy happening in ways I don't want. Okay, so if I have two 6-volt batteries, then I'm going to do a positive to a negative, and then my load is connect here and here. Now, when I do in series, both batteries are working equally. If I do in parallel, one of the batteries will loaf a little bit and the other one will work a little bit more. Not by much, but it's fine to do that. But what that does, if I do it in series, it doubles the voltage and keeps the amperage the same. And it just says here at the bottom, never cross the remaining positive and negative. Don't get confused between, was that this or was that that? Okay, so let's say there's no disaster today and I want to charge my battery. It's raining really hard. I don't want to play around with solar. And somebody might say, well, I'm just going to go ahead and grab my 5-amp charge controller that I use for regular car batteries, and I'm just going to hook it up to my more expensive AGM battery. Is that a good idea? No. Why is that not a good idea? Because it's not designed to do any smarts about that. It's just designed to bring it up a little bit and we're done. So that's not what I want to do. So and your batteries, you'll have to spend some money for your batteries, but they'll be good to you if you're good to them. Okay, so what I would recommend is something like the Battery Tender Plus. This is a 1.25 amp charge controller. This one here will work well. It's 3-stage, and then they also have the 3-amp model. So that will help you out with charging the battery. And it does temperature compensated charge, and you'll see after a while that's rather important. Okay, so the Deltran is a 3-stage charger. Now what you have is you have 3 charge phases. You'll have a bulk phase where all the current's going into the battery, and when it's getting near a set point, that's where it's going to kind of taper down the amperage. And I'm going to go into more detail on this when I talk about charge controllers. And then it'll go down to a trickle charge and probably hold the voltage at about 13.2 volts. Now, heat really affects lead-acid batteries. If you keep it for every 15 degrees above 25 C or 77 Fahrenheit, you lose 50%. So that's like constant storage. So if you had a really hot environment and you had your somewhat expensive lead-acid battery, AGM battery, you wouldn't get as much joy because you'd be buying more often. And cold just temporarily reduces how much power you'd get. Now here is a chart that I got from the Batteries Plus, anyway, the representative sent this over. This is if you had a constant temperature, a float voltage, how much life you would get. So if I'm at 104 degrees Fahrenheit, I might get about 2 years out of that battery max. If I stored at 86 degrees, I might get about 4. If I stored at 68 degrees, I might get about 6 years. That's if I treated it well. Now, your battery wants you to know that you just have to be careful because someone's going to tell you, oh, you want to take good care of your battery, just buy one of these XYZ brand trickle chargers. But if it's poorly regulated, it'll just keep rising and kill off your battery. And then there's something called thermal runaway, if we talk about safety. And that's where you have high ambient temperatures and your voltage, your charge voltage is set too high. And what it's going to do is it doesn't regulate what's really going on well. And you actually boil off the electrolyte. And then the battery temperature gets hotter. The resistance changes, and pretty soon you have a meltdown or a fire. So we do want to keep our batteries out of direct sun if we're talking about solar power. See if there's a way we can shade it some. Now something else that could really hurt you also is a short circuit. I don't know if you can see this, but right here, the maximum discharge current is 900 amps for 5 seconds with an 80 amp hour battery. So if I got a little fumbly with my screwdriver, and this one isn't going to reach, right? So I'm not going to mess up. I could get a lot of trouble happening if I short-circuited. I think you can do a lot of arc welding with 900 amps, maybe. I'm not an arc welder. Okay, so now, if you have a valve-regulated lead-acid battery, what that is there's some one-way valves in your AGM battery that will allow a little extra gases to release, but it's trying to keep a positive pressure so the oxygen and the hydrogen can do some recombining. But they're not perfect. You could have some gases escape, and what we want to know is be careful about wet cell batteries or the VRLAs, and don't put them in a sealed container because hydrogen can ignite at concentrations as low as 4%, and you can't smell it. Flooded batteries, if you have a large flooded battery bank, then you would actually want to have a way in which you enclose that and have it vent to the outside. Now, if I'm charging batteries, what I want to talk about is the ideal charge rate, a fast charge rate, and then the maximum charge rate. If I'm on solar power and I'm in an emergency, I'm not worried about getting 500 cycles out of my battery. I'm worried about having energy to get me through the night so I can keep my communications going and charge my battery up quickly starting the next day. Now, the types of batteries are the starter battery, the marine battery, and the deep cycle battery. Now, the batteries differ mainly because of the plates. So the lead acid battery, it has these 6 compartments, about 2.1 volts for each. So that gives you around 12.6 and a little bit extra. And the deeper you discharge that battery, the more those plates can bend and flex. Now, the starter battery has a whole bunch of thin plates. There's lots of room to make the chemical reactions happening. So the active materials can be really utilized well. I go to turn on my car, I get this cold cranking amps, and I just use a whole bunch of amperage for a short time. I'm done. But if for some reason you had to use a car battery in an emergency, you want to, or a semi-emergency, let's say, you want to try not to go more than about 20%, or you can start having some damage. Those thin foam plates can have some problems. So a car battery is not the battery I would buy or use to prepare for the emergency, but they might be readily available if like a large earthquake or something happens. What would happen to our road system if we had a large earthquake? How can I walk across the county? I can't go through the neighbor's field. The roads are what I've got to have. So literally, an earthquake is a come-as-you-are event. You might only have extra reserve capacity as car batteries. It'd be nice to know about how much could you probably use those. So the big Cascadia Rising earthquake happens. You could possibly use a backpack foldable solar panel. This is an AquaPower 50-watt solar panel right here. You could put this in your backpack, and you could go ahead and get a charge controller and a radio and some things. And let's say you don't really have access to a lot of battery. You could then take a car battery and try to keep it going. Okay, so a typical car battery, they talk about cold cranking amps, but they don't really list them as amp hours. And so the typical car battery is around 45 amp hours. And if I was using the top 20%, that means I have about 9 amp hours of available energy before I start really having the plates start bending and having some problems. So I take all this gear with me. I go into the scene. And let's say I'm going to be talking a lot more. I'm going to talk 20% of the time, listen 80% of the time on medium power. So I transmit at 20 watts, 4.5 amps. I receive at 0.3 amps. I put that all together. My overall average amps is about 1.14. The sun is shining. And this solar panel, it's a little overrated on what it says it'll give out, but it will do about 2 amps. I could be going all day if I walked into an area that had no communications and I said, I'm the communications volunteer, I'm willing to go to this unentered area after the earthquake because we don't have any amateurs there, but we want communications. We can get there, but we have to hike and bring our stuff to the scene. And if I needed more amps, I would just get another foldable solar panel to go to my backpack. Now, we can charge the starter battery 10 to 20%. If the car battery was about 50 amp hours, my charge current can be about 5 to 10 amps. So that's about how much I can use. And then if I wanted to do more, I could parallel some car batteries. And I'm going to talk about that in charge controllers. Now, after dark, I could still use that car battery. Let's say I'm going to talk about 10% of the time, listen 90% of the time, and I'll stick with medium power. I've got a good antenna that I brought with me. And so I'd have 4.5 amps of transmit. I would have 0.3 amps receive. Overall amp load about 0.72, it's a little less. And I got 9 amp hours of available energy. So I could go about all night if it was a 12-hour night. And then sunrise the next morning, start getting some energy from the sun, and I could keep going. I have to utilize the resources that I have in an emergency because that's all I have. I didn't have an opportunity to have anything else, but if I had a few of these items in my kit, then I could be more flexible to go into some areas and know that there's those car batteries, I could put them to good use. Now, when a lot of people go out and work in the field and have some practice, they come home and charge their battery up, and they're not as worried about what we call round-trip efficiency. So if I have a 100 amp hour battery and I take out 20 amp hours, can I just plan on putting 20 amp hours back in and I'm full again? No. So for a lead-acid battery, I'm told that the round-trip efficiency is somewhere around 20%. And let's say I took out 14 amp hours. I would have to take that times 1.2. I'd have to be seen on my meter, maybe, somewhere around 17 amp hours going back in to make up for that efficiency loss. It's not 100% coming back. Lead-acid batteries, not so efficient. Lithium iron phosphate, they're actually a bit more efficient. Oh, let's go to the marine battery. So these are batteries that the plates are thin enough that they can talk about them in cold cranking amps. There's more surface area for the active materials to give you a lot of cold cranking amps. But the plates are thick enough that now you can start to deep discharge a marine battery some. But it's a hybrid battery. It's not a deep cycle battery. And they're good for deep cycle for about 300 to 400 cycles. It's a compromised battery for our purposes. And it's not a battery that I'd buy brand new. But if someone that I knew had a used one and they were giving me an amazing price, and I'm just starting to build out my station, I'll take that. Okay, deep cycle battery is what we do want. And they say for lead-acid batteries, you should plan to not deep cycle more than about 80%. You'll get less life out of the battery, but at least you're not going to cause some extensive damage to the battery. Now, I recommend still that you go down about 50%. Now, within the deep cycle battery family, there's basically 3 models. There's the flooded battery, not very ideal for what we want to do. The gel cell, really not ideal for solar. I'm going to tell you why. And the absorbed glass mat, that's the one that you want. So the flooded lead-acid battery has a little bit higher top-off charge. And they're filled, of course, the lead acids with about 65% of the water, 35% sulfuric acid. So you have this risk that if somebody stumbles and knocks your battery over, If you do spill, just have some ammonia nearby to neutralize it some. They're cheaper to buy, so if you're looking at batteries strictly from a price point of view, you might be tempted to go that route, but I wouldn't recommend it, and they have a little bit higher self-discharge, up to about 15%. Gel cell batteries. These are nice for a particular application, but for solar power, not so nice. They need a lower top-off charge, but the biggest problem with them is you can't charge them too fast. If you charge them too fast, they form gas pockets and they don't heal. So you damage it and you try to be in an emergency, and suddenly your capacity is falling off because you tried to make it do something it was never designed to do. The battery that's designed to do better, if you're in the lead-acid family of batteries, is the AGM battery. So, would I buy a gel cell? Never. If someone gave me one in an emergency, I'll be happy to use it, but I know I can't try to recharge it too quickly. Now, absorbed glass mat is what we would want if we're in the lead-acid battery family. And it uses fiberglass polyester mat separators between the lead and the lead dioxide plates. You have these 6 different chambers with all these plates. And what they do is they take the electrolyte and they have a starved electrolyte, so they don't have a bunch of sloshing around. So the mat is filled up with the chemical, so your active materials can do the work, but now you don't have this moving around all over with the stuff, the lead acid. Okay, AGM batteries. They're safer. They don't need watering. The self-discharge is about 3%. And then how long you would go between storing the battery and charging it up, I'd want you to check with your battery manufacturer. I think there could be a lot of variance there. Now, if we're looking at C rates, and I'm thinking of C rate is pushing or pulling, I would want your ideal charge current is C divided by 10. So that's 10% of your amp hour. So if I have a 100 amp hour battery, C divided by 10 rate is 10 amps. If you charge it at 10 amps, you'll get a lot of life out of it. You're not concerned at all. If you want to get things moving a little faster, and it might slightly shorten the life of your battery, you could do a fast charge current of around C divided by 5. And then what I want you to know, when you buy an AGM battery, I want you to see what is the manufacturer's recommended max charging current. For this battery, it's 0.25 C, this Duracell. The reason I want to know that is because if I try to charge this any faster, it's going to kick my voltage even higher, and I'm going to start hitting what's called a set point, I'll talk about in a bit, and I'll make a bunch of heat. I'm not going to be doing myself a lot of good. In a solar application, in an emergency, I want to be able to charge my battery pretty fast, but I want to know the limits of what I can do with that battery. Now, more incorrect information. This is probably something that you can chuckle about. This says, can I charge a 12-volt, 7-amp-hour battery with a car charger? Yes, you can. A 12-volt car charger can charge any 12-volt battery. And this guy has a scooter at 7 amp hours. And he says the car battery is hundreds of amp hours. So someone who's reading this might think, oh my, I can use anything to charge 12 volts? And those car batteries are just massively large. So a 12-volt car charger for a car is not okay for any of your 12 amp hour or your 12-volt batteries. And a 7 amp hour scooter battery, ideal charge rate is 0.7 amps. If I was trying to fast charge it, it might be 1.4. And of course, the car battery is not hundreds of amp hours. So let's look a little bit about lead-acid batteries. An 18 amp hour lead-acid battery, this right here, I want you to see what that looks like. So if I go down to my local store, it's about $60. The weight is 12.4 pounds. The available energy is about 9 amp hours. And when I key up the mic, I probably shouldn't try to do more than about 3.6 amps. And if I'm going to fast charge, 3.6. If I'm going to do ideal charge, 1.8. And I would try to limit my depth of discharge to 50%. So I could take an FT7900 radio on receive at 0.3, transmit at 3.1. That gives me about 10 watts. I could talk 10%, receive 90%. And what I have here is 0.31 weighted average, 0.27 weighted average. Together is about 0.58 average amps. And I don't want to go much below about 40%. So if everything was perfect and the stars all lined up, I might be good to be somewhere around 12 hours. But I'm on low power. So it's nice to get a little bit bigger battery. Here's the 35 amp hour battery. It's at $95. It is about 25 pounds. Available energy is 17.5 amp hours. Recommend the peak load about 7 amps of pull and charging 7 amps. Ideal charge would be 3.5. Now what's interesting here is this is 7 amps, but I could charge at 7 amps. If I introduced a 100-watt solar panel, this is a 100-watt solar panel, and this is a 100-watt solar panel, these in full sun will give you about 5.5 amps. So what suddenly can happen is I don't have quite as big a battery as I want, but the sun is shining, and now I'm going to get 5.5 amps here, and I can pull 7 amps here. I suddenly can do high power VHF. That is a game changer. Now, my radio station example, the FT7900, I'm going to go up to medium power this time, talk 10% of the time, listen 90% of the time. My weighted average is 0.69. I might get around 24 hours. But that's without no solar. And now the 55 amp hour battery, this is about the biggest size that I would like to have folks get. If it's any higher, you're going to have a chiropractor bill. I'm really concerned because I almost hurt my back once with a 100 amp hour battery, and I'm down to 55 amp hour. Okay, so this battery right here is $160. It weighs 42 pounds. I think the 100 amp hour were around 75, 80, somewhere in there. I mean, that's just too much. I'm a NICU nurse, so I lift babies. So that's too much for me. So available energy, now I'm getting a little bit better on my available energy. It's 27.5 amp hours, and I can have a load of 11 amps. Now this is where it really starts getting fun. If I parallel these two 100-watt panels, I've got 11 amps of solar and 11 amps from my battery, and suddenly I have 22 amps available in my circuit. I suddenly can take this 55 amp hour battery in full sun with two 100-watt panels, and I can run my HF station and have a lot of joy. Okay, so we want to go down no more than about 50%. Fast charging would be about 11 amps. That's where I'm saying fast charge would be two 100-watt panels. And that's with a PWM charge controller, not an MPPT. And I'm going to talk more about in charge controllers. But the other thing is, just one 100-watt panel is absolutely perfect for this 55 amp hour battery because that's at the ideal charging rate. Okay, my 55 amp hour battery, use the top 50%. Just talking about full power down to 40%. Try not to go below 11.7 volts. Okay, so I have I think this is just talking about the same thing here. I could double up with batteries, and I could get my 11 amps. Okay, so here's an FT7900 radio at 0.3 amps, transmit at 2.4, my weighted average 0.5. I now take low power, and I can run this off this battery for about a little over 2 days. If everything was perfect. It has to do with temperature, the state of charge when I started. But that's just an approximation. This is just a benchmark. I would want you to go out and check and see for yourself what you thought. Now, everyone knows about the Anderson power pole connectors. Remember when we used to have the Molex? Did you ever have your radio turn off, turn on, the connector didn't work too well? Mm-hmm. I've had really good luck with these. The Anderson power pole is great. I really like that. Now, of course, they have the 15 amp for that size wire. They have the 30 amp and the 45 amp, and they all will connect together. This battery is a battery that I think of as made for ham radio operators. Bioenno Power came out with these batteries in about 2010. They started, the batteries went to market in 2012. They've had 7 years of feedback, and it's designed to supply our 12 volts. In fact, it's a little generous. Those 4 cells, those lithium cells, actually run around 13 volts. So that's very helpful. There it is. Okay, now, the lithium iron phosphate batteries are showing a lot of promise right now, and people are starting to think about, what if there's a big storm and I lose power? They want to think about household storage. And people, when they first hear about lithium iron phosphate batteries, they get really scared because they remember the stories of 3 years ago. Have you all heard the story about the battery that exploded and everybody said, we're in trouble, I won't go near those? Those were LiPo, lithium phosphate, and what these are is lithium iron phosphate, and that's a very stable bond. These are different. Now, the advantages of using lithium iron phosphate batteries, they're much lighter weight. I'm going to be going through the statistics in a moment. They're smaller size for the same amount of energy. You can now go down to 100% depth of discharge. Bioenno Power slightly overrates these, so you can do that. They have a longer lifespan. How would you like to have 2,000 cycles? Versus an AGM is 500. And my AGM, I can only go down 50%. It's a relatively flat discharge curve. I have an example that I will be able to show you. And it can have pretty high sustained current. It doesn't vent any gases. It's much higher efficiency on the round trip efficiency. And you can partially charge this and put it away and go do some other things that you want to do and enjoy life, because your lead acid battery, I used it for a while, but now I got to charge it back up. Or I'm going to have my lead sulfate turn to crystal form. My lithium iron phosphate, I can charge it down, put it away, come back and use it again later. I'm still happy camper. They'll charge faster than a lead acid battery, and there's really no absorption phase. I'll talk more about that with charge controllers. There's not a lot of maintenance issues. You can use them safely indoors. They're a bit more efficient in colder temperatures, and they tolerate the warmer temperatures better.
Can you give us some specifics, like how long you can store them without needing a temperature?
They'll self-discharge 3% a year, and I think they recommend every 8 to 12 weeks to go ahead and top it off. They like to keep the cells balanced. The biggest thing about these is if you go out quite a ways, you want to do some cell balancing as you're going up and down with use and recharge. These batteries, when you do charge them up, it is important to give them the full charge so we get good cell balancing. Oh, thank you.
Do you require a special charger for the lithium iron?
Yes, yes. You do have to have a different charger than you do with lead acid.
Sir, that battery did not get here. I don't know if it's the whole.
Uh-oh.
I don't know.
Okay. This battery has not gone where? Okay. Let's go right over here. I am so sorry. Please forgive me. And then I want to keep going here, because if I get too many questions, I have a lot of material to cover, and please forgive me. I want to keep going quickly here. So what are the claims that industry is making about these type of batteries? Sony has one. I don't know if it's called the Fort Leon. It's an LFP battery that will have 74% of its rated capacity after 8,000 cycles to 100% depth of discharge.
Wow.
Now, I didn't see any documentation about that, but this is what they're making their claim. And this is where you can go to see more information. Now, that same battery will do 6,000 cycles at 100% depth of discharge and still have 80% of rated capacity. So you had 8,000 cycles, 74%, 6,000, 80%. And they're claiming a service life of 20 years. Now, these are the big ones for the household. This is not the amateur radio variety I'm talking about. But it's a new chemistry, and I'm trying to kind of get a feel for what are the claims that the manufacturers are making. Have you heard of the Simplify? Raise your hand if you've heard of Simplify batteries before. Okay, just a few. Okay, so these batteries are the bigger batteries. They're saying you'll get a 10,000 cycle life at 80% depth of discharge, 5,000 at 90%, and 3,500 at 100%. This is off of their material. And they're going to give you a 10-year warranty. This is for folks that have off-grid solar or battery backup grid tie. They're estimating a lifespan on a battery, which seems completely crazy, of 15 to 20 years. It's still a new technology. And then when they talk about a cycle, it can be more than one cycle in a day. It could go up and go down, go up and down. Okay, so for our purposes, we're interested in someone that's making a battery that is amateur radio friendly. There's probably different folks out there. I only want to speak about one that I have some familiarity with. The Bioenno battery can use 90%. You could go up to 100%. And all of these batteries have, every lithium iron phosphate battery has to have what's called a BMS. I'm going to hold this like this. It has to have a battery maintenance system. And this particular battery has what's called a PCM. Now we have to learn new words with this new technology. First time I heard it, I thought, man, there's a lot of alphabet I got to learn here. So PCM is the protection circuit module. It's intelligence built into the battery, and it has 5 functions. It has overcharge protection. It'll turn off the input if I try to get too much charge into the battery. It has over discharge protection. It protects against the guy who was talking so much, he forgot his battery was going down too much. It's going to turn off. It's got over current protection. If I try to do too much current, nope, it's not going to hurt the cells. So it's trying to protect your investment, because you're going to spend about twice as much as an AGM. You want to protect your investment. This chip is going to try to help do that. It has built-in temperature protection. If the temp rises too high, it's going to turn it off, let it cool, come back on. And most importantly, it must have cell balancing. So the high voltage disconnect for this battery, the Bioenno batteries, is around 15.4 volts, plus or minus 0.5. The low voltage is around 10 volts, plus or minus 0.5. And this is per Kevin Zanjani, Bioenno representative. To the maximum input for the battery. You just can't hook it up to a regular power supply and have a nice day. The PCM will trip and they're like, uh-oh, what did I do wrong? So you want to make sure you have an appropriate charger for an LFP battery. You want one that has a little bit of feedback where it tells you, I'm almost done charging, I turned on my green light, now let me go for about 15 or 20 minutes. Now, if it's late at night and you want to charge the battery, don't worry about it. Just put it on, leave it on overnight. The green light will be on in the morning. You can disconnect it and have a nice day. So it's not like I had to wait for that 15 minutes. You just want to make sure you at least give 15 minutes. Okay, so switching power supply for the 30 amp hour battery. 14.6 volts is what it says. It's 15 volts, 6 amps, and it turns off. This is for the 30 amp hour battery. Now I could, if I had one that had terminals I wanted to clip to, but if you do get the charger, go ahead and make sure you get this little connector to Anderson power pole. That's going to make your life more joyful. And this one here will have the light right here. And just watch it as it stays red. It just hit green. Make sure it's at least on for 15 minutes or more, and then go enjoy yourself. Have a great time with your radio. But you do need to top it off from time to time if you're using it a bunch. Okay, they recommend that you probably do this balancing at least every 8 to 10 weeks. And if just using solar, this is a little more technical, but if I'm using solar, the panel is going to slowly come up and it's going to have time to do the cell balancing. And I'll speak more about that when I talk about charge controllers. So here is an interesting example. I'm just getting started out in amateur radio, and they told me that if I want to play with my radio not in my car, I got to buy a power supply. Now, if I don't use my radio that much, I could take this power supply, hook up my radio, hook up my battery, and the battery that you're passing around, that's a 20 amp continuous. It'll support through the whole cycle. You could go ahead and play with your mobile radio, have your power supply going. It'll support every time you hit your transmit. Just you won't exceed 12 amp hours and whatever time you had while your 2 amp power supply was going. I was actually going to visual this, but you'll just see it from the slide. Okay, so a flexible power source for your portable radio. You put that 2 amp, you put the 12 amp hour battery, you put it together into the distribution block. And what you could use is a West Mountain Radio 4004U. It's a nice little distribution block. And you could just, because there's no fuse on these batteries, the way they come like this. Now, once this battery is in this power box, which I'm going to talk about in a moment, then your fuse situation is taken care of. So if you get a distribution block and you want to hook radios and stuff, try to get a distribution block that has fuses. You want to make sure you're safe. You fuse your circuit. Okay. So this was just basically saying, if I was able to do the demonstration, that if my radio was on receive, my 2 amp power supply and my LFP battery, if my radio only needed half an amp, 1.5 amps could be charging my battery while it's in receive. And then when I hit transmit, the power supply will give 2 amps and the battery will give a certain contribution. And I have a slide right here. This slide right here, the top left inline meter is showing that it's providing 2 amps. The battery is providing 3.23 amps. And I had like a medium power load on the TMV7 of 5.25 amps. And this is also true for solar. When we hook up the battery and the solar panel, all the solar amps is going to go to your load. And if the load doesn't need that much, the excess is going to go to your battery. So while you're listening 90% of the time, you're charging your battery. And then the solar contribution plus the battery will meet your peak load demands when you hit transmit 10% of the time. Okay, the PowerWorks box. So you can put, this one's designed for 30, 40, and 50 amp hour LFP batteries. And you can put this battery in here. Here we go. Now, what this has two Anderson power pole connectors on the top here. I can turn a switch on and it says how much the voltage is. I have two higher output USB, and I have my power port and I have my binding post. Now, even with this box, I would like this gentleman here again to pick this up and then pick this up.
Sure.
Okay? Now, what's that feel like?
Yeah, that feels like
Okay.
good 40 pounds.
I need you to hike about half a mile to where you're going to set up the station.
I've done it before.
Okay. Now I want you to pick this one up.
Oh, yeah, much lighter.
Can you go half a mile with that?
Easily.
Easily. Okay. Is that a game changer? That's a technology that's unbelievable. Now, the good news is, this particular box, I can take the charge controller and put it in the box. I can take 30 feet of number 10 wire and I put it in the box. And I can put two inline meters. And now I have everything I need. I just hook up my radio to this box and away I go. And if I want to charge, I hook into one of those Anderson power poles. Isn't that nice? Now, a friend of mine has an has an AGM. He made his own box here. He's got a lot of the same similar features, but it weighs a bit more when I pick it up. And some of us are getting older. I'm not saying anything. And picking up those big weights might not be good. Our doctor might want us not to have a weight. Might have a weight restriction. I can still meet my doctor's weight restrictions and enjoy my hobby. Okay. So basically, just talking, it has the two USB charging ports, two power pole connections. It has the one automotive power port, the binding post, inline meter, and it's got the fuse inside. And here it is. I've got it in my kitchen here, and I just was charging it up. And I wanted you to see it was at 14.6 volts, and the green light's on. And it's just doing its cell balancing right now. But the good news is I don't have to worry about that 15 or 20 minutes. I just plug this thing in, go to bed, have a nice time, do some things, go shopping. My battery's ready to go. Okay, so I did a charging test. I took the 30 amp hour battery, 30 amp hour LFP. I took out 5 amp hours over 140 minutes, and then I wanted it to come back up. Now what you're going to see on here is the power supply on the far right was red, the charging amp hours, how much was going in, and then if you look at the voltage, and these the time on the far left in military time. It was a late night test, as you can see. So the voltage was just slowly rising. And then watch what happens to the amps. When I get down to 1128, all of a sudden, there went the amps. It just fell off really quickly. And then I was down to, by 1148, I had 0.1 amps going in. My battery voltage was 14.5. And I basically gave back the power that I took out. It was a fully charged battery. I was just doing a test. But here's the piece on this slide I want you to see. From 1128 to 1138, in 10 minutes, it went from bulk charge to I'm basically good to go. Thank you very much. Okay, now let's do a little comparison. My 42-pound battery and my 7.6-pound battery. Okay? Here's a comparison chart. Available amp hours, my AGM, 27.5. I got at least 27 at 90% depth of discharge. 500 cycles versus 2,000, and I get more depth of discharge. My discharge curve is sloping. I got to turn down my power halfway through my joy. I got a flat discharge curve. I have to worry about sulfation with the AGM. There's no sulfation with this. I have no battery protection, but I don't need it necessarily. I just have to be a smart operator and not mess up with sulfation, grid corrosion, and some gassing problems. And I have a PCM built in. The price is about double, but if I get 4 times the life with more depth of discharge, I might see mathematically where that could be an advantage. So now let's take the 18 amp hour battery. It's 11.9 pounds. The BioEno is 3.3 pounds, the one that you're looking at that's going around the room today. The 18 amp hour AGM is 9 amp hours, and it's 10.8 at 90% depth of discharge on the little 12 amp hour LFP. No sulfation, more efficiency. Sounds like a choice to be made. Okay, so here we are. The max current on that battery that you see going around the room today, it can support up to 20 amps. The peak pulse is 40 amps or 2 seconds. The charging current up to 5 amps. And remember that that's what they're saying. And of course, if you're 0.5, it's 6 amps. Now, there's a little difference with LFP between operating temperature and charging temperature. I want you to take note. Operating temperature means I can go below freeze. I can get a little cooler, but if I'm going to charge the battery, I need to be 0 degrees Celsius or 32 degrees Fahrenheit. I can't go below freezing. Now, there is some chemistries for LFP that can go colder, but that's not what BioEno Power is putting out for us. And I bet you might pay more for specialized chemistries. That's what I would think. Okay, so I did a 4-hour load test with that same battery that you have. I put it on a load of about 2.6 amps, and every once in a while I did a little bit of higher transmit. So I set it up so like 2 radios hooked up to it, about 16 amps, and I ran it down 100% depth of discharge. And what I wanted to know was what was the voltage when I'm near the end of the capacity of that battery. So I got down to within 7 minutes near the end of the test. And when the meter said I'd taken out 12 amp hours, that's 100% depth of discharge, I put a 19 amp test load, and my voltage under load was 11.7 volts. What's my radio limit? 11.7. This battery, the way it all works out, it works nicely for amateur radio operators. A little bit better than lead acid. Okay, I'm just going to talk about USB power banks, the 5 volt. Everybody knows about these. In an emergency, you can use your extra power to charge some of these. So basic, oh, I did something wrong. Okay. Okay, so they're not designed to do what the LFP does. You don't charge and discharge. You do it one at a time. They're 5 volts. And what you can do is, if you're curious about how much you got going and what your needs are, this is a 5 volt inline meter. It's called a Droke. And here is the meter hooked up to a USB wall socket, and it's doing some charging. In the red color, you see voltage. In the blue, you see amperage. But recognize this is not a 12-volt circuit we're looking at. This is a 5-volt circuit, so 4.98 volts is your nominal 5. And what I would want you to do is think about, if I'm in an emergency, I'm charging up my primary battery, but I might have excess solar, I don't want it to go to waste, charge up some of these. So then when folks are out in the field doing emergency with their phone, their camera, their calculator, their first aid app, you're not going to ask the emergency worker to give you, hey, can you give me your cell phone? I'll charge it during the day and I can give it back tonight. No. You'll charge these up, give it to him. He'll charge his phone overnight because he needs time to bring the charge up. And so you help support your incident command team by helping keep their devices going. So that's a big help. So what I want you to do is go ahead and do some tests with USB power banks and see how much they would need. Now, the 20 amp hour, this one right here, remember this is 5 volt we're talking about. This 20 amp hour, when hooked up with a USB buddy, that takes 12 volts, converted from 12 volts down to 5 volts, requires 0.93 amps at the moment that I took this picture. So about 1 amp for every big USB power supply. I wanted to see if there's parasitic loss with the USB buddy. And I might have it here somewhere. I'll find it at some point. So the USB buddy is a very nice device for being able to take 12 volts and step it down to 5 volts, and you can connect it directly to a solar panel. Now, the input voltage on the USB buddy is 10 to 32 volts. Outputs is 5 volts, 3 amps. Uses Anderson power poles. And then here's the Petzl core battery that I was talking about, and I've got it in one of the headlamps. This little battery can recharge. It's the size of AAA batteries. It can recharge 300 times. It's rated for. And this is a little bit more information on the back. So recharge up to 300 cycles. Since 2018 on, Petzl headlamps, so if you're doing task lighting, you have one of these, I think they're maybe $30 or something. You can recharge in an emergency. That's what I wanted to look at, is things like that. So the Petzl core only needs about 0.22 amps in a 12 volt circuit. So every Petzl needs about 0.2, every large USB needs about 1, and you could get an idea of about how much you would need. And this is showing the red light as it's charging, and now it's full.